Today we're going to be talking about Panda, or near optimal latency versus cost trade-offs in geo-distributed storage. So this paper is all about global storage, right? So let's, for a second, assume that we have these 3 storage locations, right? So we have the storage locations. We can write some documents, some data to the storage locations. And then we have a client, and this client wants to interact with the storage system that is comprised of these 3 storage locations, 3 storage servers, so to speak. And this client, she can write her document, she can write her data to all of these 3 locations, right? So when she does that, she can then read the data from just a single instance, single storage node. Right, so by the virtue of having this writing to all of the storage locations, now we can see, now we can read from one because her write set, or write quorum, is now intersecting with the read quorum, which is just one node in this case. So this is really good if you want to optimize for a read performance, right? For a read latency, you can have this storage system next to every client that you may have, so that they can read data very quickly. Now, of course, the problem is, right, we have to write the data to all of these storage nodes. And there is another caveat with, how this data should be available to you. So for a second, so this is like the second client, right? So, we can place them. The data is quickly available, by the virtue of us being able to read from the closest node. So the caveat is, we want to make this a strongly consistent system, like a linearizable system. So it's not enough to just write the data to all the nodes so that you can then read from one. So there is this notion that every node it kind of needs to be aware of whether the data has been globally written or not, right? So let's say I have this client right here, somewhere in Europe, I guess. Yeah. So she is writing this red document to this storage system, right, located in these 3 different sites. And she happened to write this red document to the 2 sites out of 3. At the same time, a different client comes in and tries to read, from that one node that she's supposed to read from. Now, which version of the document is she supposed to get? So if she gets the red version of the document, well, the red has not been written globally yet, right? So we may end up in a problem where she reads this red document and then she does another read and somehow goes to a different node and reads the old data. So now we just broke the strong consistency guarantee. We broke the linearizability because we all of a sudden were exposed to the stale data because this red document is still propagates into this storage server. So this caveat is kind of important, for overall like read-write strongly consistent systems. So another problem, of course, is we had to write to all the sites, right? So this write operation is really slow, because like you have to wait for this data to be replicated to all the sites. And on top of that, you also have to kind of then tell every site that, hey, the data has actually been applied to every site. So you do have to wait quite a lot just for you to touch every single site. So instead of writing to all sites, right, we still write to all sites, but we may want to wait for a smaller subset of all the storage nodes, or a smaller quorum, right? So in a system of 3 nodes, for example, we may pick a majority quorum system where just 2 out of 3 nodes, any 2 out of 3 nodes, is going to be enough for you to consider the operation completed. So if this user writes this data, she only needs to wait for her 2 closest storage sites, while the further site will eventually get the data, but like she is not blocked on this site receiving this data. So we can essentially improve the performance of our write operations. unfortunately, it comes at a cost, because now it's not enough for us to read from any storage node, right? Now, like if I try to read from this guy, it may or may not have the data when the operation has already been completed by the smaller quorum. So just like in pretty much every single quorum system that we have that tries to provide some sense of strong consistency guarantees, we do want to have this read quorum and write quorum intersection. So this client, she will now need to read from 2 sites instead of just 1 site. So if you see, right, we can kind of trade off the write latency. We can improve write latency at the expense of making the read latency higher, because now we have to reach to an additional site that may be located further away. So essentially, like we operate in this trade-off, and this trade-off is really rooted in the geography of your system, right? Where your sites are and where the clients are. So, for example, if I have a client here, right? So reducing the quorum system actually didn't buy a lot for this client, because now if she wants to read, her read is now super slow, because she needs to reach one of the 2 sites that are super far away from her. And her write latency has not really improved much, because instead of reaching 3 sites, she still has to reach 2 sites, and these 2 sites are about the same distance away. So her write latency hasn't improved. Her read latency tanked by a lot. So us trying to achieve this compromise between read latency and write latency, we, in this case, right, in this example, we have succeeded for this one client and improved her write latency by somewhat degrading her read latency, but not too much. But we completely broke the performance for the other client just because of her geography and the geography of the storage nodes. So this read latency and write latency trade-off is kind of 2-dimensional, and that's one of the trade-offs that Pando, the system that this paper talks about, really considers in trying to optimize, right? So trying to find the balance between the two. So the way they try to find this balance is, they say, well, if this client is now at the disadvantage, what happens if I add more storage sites, right? So I can add more storage sites close to my other users in such a way that maybe I can form a read quorum out of the storage sites that are close to this user, maybe a read quorum out of storage sites that are relatively close to this user, so that everyone is happy with their read performance, right? So, and this is essentially how Pando works. It adds more storage sites in the geographical locations that are favorable for the users, right? So it considers, I believe in the paper they run, they did experiments on Microsoft Azure, so they consider pretty much every Azure data center as a potential storage site, and they just decide which storage sites to use for particular object or document or whatnot. So in this case, right, by adding just one more site, this client can now have a read quorum of 2 nodes that is fairly small, fairly quick, not far away from her. This client can read, can get her quorum, read quorum of 2, also somewhat okay. And again, this comes at the expense of the write quorum, right? So the write quorum is now 3 nodes, because we have to remember, we have to have this overlap between read and write quorum. So, but even this write quorum is not actually that bad, excuse me, compared to the 3-node scenario that we have, because for this client, this 3-node write quorum is still better than 3-node write all quorum that we originally had in the very first example, because it's a little bit closer to her. So we did improve a little bit of the performance for writes, while significantly improving the performance for reads for this guy, and still having maybe an okay performance for read for this client. So yeah, Pando adds a lot of sites. So this actually adds another dimension to their trade-off. So we are no longer talking about just the read and write latency trade-off. We also now have the trade-off in terms of the storage space, right? Because by adding this one more site, essentially, I increase the capacity requirement for storage by 1/3 of my initial 3 storage service setup, right? So, but if I add 5 more nodes, I can have a lot of nodes. Obviously I store more data. So this is where the Erasure cousin really comes into play for Pando, as it tries to use this Erasure cousin to really manage this storage problem, right? So write amplification. So I'll come back a little bit more to the Erasure cousin towards the end of my presentation, but surprisingly, it wasn't really that big part of the system here. It just, this mechanism that allows them to keep the storage cost under control while adding a lot more storage locations into the system. So what is Pando in a nutshell? At least, the way I see it, my understanding of the system is that it's a flexible Paxos. Flexible Paxos with a few really interesting twists and additions to it. So just like a regular flexible Paxos or regular Paxos, it's a two-step, two-phase protocol. So when a client needs to write some data, this client, is a proposer in this Paxos system, and she will say, "Hey, can I can I write this document with version V?" And she will talk to her phase 1 quorum in this flexible Paxos kind of system, which doesn't have to be a majority, right? So it can be a small quorum, which actually is the same quorum as the read quorum in a traditional read-write quorum system. So she talks to her phase 1 quorum, and they will say, "Sure, go ahead." In a happy case scenario, obviously, right? So when she receives this go ahead, when she becomes the leader for this particular document with version V, she will replicate this document to a write quorum, a phase 2 quorum of storage sites. So this is how the regular flexible Paxos would work, right? So phase 1, get the leadership. Phase 2, replicate the data. Happy case of flexible Paxos. So what Pando does differently is it tries to optimize the latency in this flexible Paxos protocol, because you can see that it's quite chatty, right? So she talks to all these guys, then she talks to all these guys. So in Pando, our client, our proposer, she sends the phase 1 message, to her read quorum, phase 1 quorum, but she picks one of the nodes in my diagram here, this pink node, as the delegate. So this delegate is going to be responsible for collecting the phase 1 votes. So while she picked this node as the delegate, she also sends the document that she wants to write. So this delegate will receive this document, and it will just buffer it and hold it for now. It's not going to apply this document to a storage or anything until it receives the quorum of phase 1 accepts, right? So if this node then replies back to finishes the phase 1, replies to the delegate and says, "Sure, go ahead. I don't have any other version that may need to be recovered." When this happens, this delegate, the pink node, can start replicating this document in the phase 2. So if you see the latency, we kind of cut the latency here, because for her to talk to this pink delegate, it takes quite substantial time, and it takes a little bit less time maybe for this other node to talk to the delegate, but it takes very little time for her to talk to this node. So a lot of this acknowledging can happen in parallel with her initial phase 1. So this node will start acknowledging that it's good to go for phase 1, maybe before this node even received the phase 1 message from the proposer itself. So we do have like a little bit of a race here, but eventually you receive all this stuff, and you'll be like, okay, I'm good. I'm the delegate. I have the document. Everyone agreed. I can proceed to phase 2. And phase 2 is, this delegate is essentially sending this document to all the replicas, right? All other storage nodes. And again, it doesn't need to wait for all of them. It just waits for this write quorum or phase 2 quorum. And well, it sends this document, but the reality is it's not even waiting for the replies back, because this guys, the other replicas, they're instructed to reply back directly to the client, so that we avoid this relaying again. So they can reply directly in hopes that this is going to be like the shortest route instead of going through the relay route. So this whole delegate situation, right, and allows you to mask a lot of this phase 1 latency and improve slightly on the phase 2 reply latency. And the authors of the paper, the authors of Pando, they claim that with this delegate approach, they come very close to the latency that would have been achievable in just one round trip from the client itself, right? So this 2 round trip regular Paxos protocol, they claim that it comes close to the latency of 1 round trip protocol if it was driven directly by the client. So this is where they save a lot of the latency. So that's like, in my opinion, they're one of the most important optimizations. Now, there is another important thing to consider, right? Is that like here, I haven't really talked about erasure codes, but as you add more nodes, you start to do the erasure codes and to save on the storage cost. And for example, if you have an erasure coding system that splits the data into 2 partitions, 2 splits, right? So that's k equals to 2. That actually means that now you have to change the quorum intersection, right? So instead of having 1 node to intersect, you need to have 2 nodes to intersect in your quorum. And that's because you need to have 2 nodes to reconstruct the data, right? So if you have only 1 node, you don't reconstruct, you don't have sufficient information to reconstruct the data. So 2 node intersection is important for data reconstruction. If you have just 1 node intersection, you will know that there is a newer data, that something has been written, but you will not be able to reconstruct the data. So, and that's kind of the second trick in Pando's sleeve, is that it first tries to run the protocol like with the smaller quorum, right? So it hopes that 1 node intersection is enough, to guarantee that I observe the latest version. But it also hopes that other nodes that were not originally part of the write quorum, by the time the read has happened, have received this version, so that you have at least 2 copies of the data, despite having only 1 node in the intersection. And of course, if this fails, then they wait for the other nodes to come in until they have this enough nodes in the intersection between the read and write quorum. But yeah, the point is this intersection depends on the number of splits in this erasure coded data distribution. So that's pretty much it for Pando. Like at least the way I understood and probably oversimplified it a little bit. It's a flexible Paxos with some neat tricks to reduce the latency with the delegates, and some neat tricks to have the smaller quorum in a happy case when we do use the erasure code. So you don't have to wait for all the k nodes to the quorum intersection. So there are a lot of assumptions in the paper itself, and a lot of things that I wish they have talked a little bit more, right? So obviously, for this thing to work, the assumption is that the read is going to happen most likely when all the data has updated. So they don't expect a lot of these conflicts, for the performance reasons. Similar way, they don't expect a lot of clients to try to become leaders on the same document at the same time, because this will lead to the dueling leader kind of problem, where they try to outnumber each other, and none of them is going to go into the actually writes in the document. So the paper actually talks about some of these scenarios, right? So they talk that sometimes if this happens, it's okay to violate our like their internal metrics for write latency. So the write SLO, it's okay to violate it occasionally in case of these conflicts. But they also say that in their kind of mindset, in their scenarios, the conflict rate should be very small. So the performance evaluations, I guess what's interesting about the performance evaluation is that they have come up with this theoretical lower bound latency based on the read-write quorum kind of system. And they show that their system, Pando, actually comes very close to the to the theoretical system, and significantly outperforms ePaxos, which they set up as the main kind of geo-distributed Paxos-based competition to Pando. So yeah, latencies, overheads, and obviously, like all of these graphs, right? They kind of come in the context of where of this trade-off. Where do you set your expectations for writes? Will adjust the requirements for read. So if you want super short, super small, super fast write, then the read is going to be smaller, slower. If you want fast read, then the write is going to be slower. And if you kind of try to find the balance between the read and write, then you may have a higher storage overhead. So a lot of the evaluation actually concerns with finding these trade-offs, which you can look in the paper. But what I want to point out is that it seems like Pando is coming very close to that theoretical lower bound system that they have estimated. Because Pando also cares about the cost, right? So storage is expensive. Having more nodes is expensive. So they do have evaluation to break down the cost basis of their system. And again, based on the cost and like different configurations, different sizes of objects, Pando seems to come on top of the remaining systems, except maybe in this very large storage with in this particular configuration where the network for Pando is quite large.